an atom has an atomic number and a mass number. So for example, sodium has 23 as its mass number and 11 as its atomic number. 11 means there are 11 electrons and 11 protons. 23 means there are 11 electrons, 11 protons, and 12 neutrons. So basically, the number on top equals the number of neutrons plus the number of protons. The number on the bottom equals the number of electrons or the number of protons. So if you want to work out how many neutrons there are, you do the number of both of them, so neutrons and electrons, minus the number of electrons, which is 11. And that will give you what's left, which will be the number of neutrons, because then we are taking off the number of electrons there. Okay, so that gives us 12 neutrons. Alright, so that is about the mass number, which is the top one, and the atomic number, which is the bottom one. Now, this is important because it tells you the number of electrons that should go into the shells, which also tells you how likely each thing is to form an ion or to form a covalent bond. So let's look at the groups. So groups 1 and 2. That just means that group 1 has 1 electron in the outside shell. Group 2 has 2 electrons in the outside shell. Because there's only 1 or 2, they want to get rid of them. Anything that gets rid of an electron becomes an ion. So group 1 and 2 are more likely to become ions. Okay. So group 3, 4, 5, and 6 are more likely to be covalent because they have more. So they'd rather share them than get rid of them all. So on the other side of groups 1 and 2, you have groups. Actually, 6 isn't, so 6 and 7. So, if we look at them, they almost have a full shell. They almost have 8 in their outside shell, because group 6 will have 6 electrons in its outside shell, and group 7 will have 7 electrons. This means that they only have to get plus 2 electrons and plus 1 electron to form ideal gas outside shells, which is 8 electrons. And that would be group 8, obviously, because the number of electrons in the outside shell is the group number. Alright, so if we look at that, we can work out that certain ions are likely to form. So for example, sodium. It's in the first group. So if it has 1 electron in its outside shell, it's likely to get rid of that, which means it's losing 1 electron, so it's left with 1 positive charge. And chloride would be formed from chlorine in the 7th group. 7th group means it needs 1 more electron, which will mean it's Cl-, so that's why you get NaCl. Alright, so isotopes are kind of similar to ions in a sense, because they have different numbers of a sort of subatomic particles. So the subatomic particles are electrons, protons, and neutrons, and they're called subatomic because they're below the atomic level. They're smaller than the atomic level. So if we look at this, there's carbon 12 and there's carbon 14. Now these are the mass numbers, not the proton or atomic numbers. And the mass numbers are the number of neutrons plus the number of electrons. Okay. So C12 is the common one, common isotope, and it means it has 6 neutrons because it has 6 electrons, and if we take 12 minus 6, we're left with 6 neutrons. Okay. So that's the most frequently found one on Earth, and C14 is the other type. It's less frequently found, and obviously C14 has the same number of electrons, but this time we have 14 minus 6, which is going to give us 8. That's the mass number, which is neutrons plus electrons. This is the atomic number, which is just the number of electrons or the number of protons, because they're equal. Okay. So once things form chemical bonds, they're not likely to detach. That's why it's so hard to get minerals out of compounds in the earth. That's why reduction, oxidization, and mixtures of acid are needed to get rid of those compounds that are attached to things like iron or aluminium that we need. Okay, so ionic compounds, they form really strong structures, and you need to remember that they're called regular lattice structures. So for example, for sodium and chloride, what you have is something like a whole group of plus and minus ions. So just imagine the pluses are sodiums and the minuses are chloride ions. And they just form these boxes, and they're all attached, and they go in 3D as well. So you have plus, minus, plus. And the reason they stick together so strongly is because they're opposite charges. Okay. They're really hard to break apart. They have electrostatic forces. Electro just means charge. Static means fixed, not moving. Just like static electricity means it's not moving. So it's still or fixed. That's why they are much harder to break apart than covalent bonds often are. And you can call it a giant ionic lattice. Apart from being a regular lattice, it's also called a giant ionic lattice. Alright, so they have high melting points and high boiling points because that means it needs a high amount of energy to break apart. Well, obviously this is going to be a solid as well because it's stuck together. The atoms can't move, the ions can't move, I mean. Well, if you do have a high melting point, it means a lot of energy is needed to allow them to move, because obviously melting is going from solid to liquid. And in order for them to become liquids, you need them to be further apart. But they have a very strong charge between them, and that's called the electrostatic charge. So more energy, more heat is needed, so a higher temperature is reached, a higher melting point. So now if we imagine those two are atoms, then we can see why the electron shells are drawn differently to the nucleuses. Because electron shells are drawn as kind of circles around the whole atom, and the nucleus is one thing in the middle. This just shows you the electrons are all over the place. So in reality, electrons can be meters away from atoms. They can be ages away. So these two atoms could just have electrons floating everywhere. So in reality, these electrons are going to be in shells of energy, but they might not be right around something really closely. They might be all over the place, and the shells might form strange patterns. But if you think about it, if this was going to form a negative ion, then it would take the electron that's closest to it. So it would take the electron that's closest to it, and the electron that's closest to it will be in the outside shell. So it would be in the outside shell of the drawing. This is just to show you the drawing doesn't show you exactly what it is in reality, but that it does show you the outer shell is closer to the other atom, which wants to seal the electron. Okay. So ionic compounds, which all form giant ionic lattices, have high melting points, high boiling points, and they have a strong attraction, which is called the electrostatic attraction. They melt, and then the ions are free to move. And when ions move, they're just like charge in a wire, because charges in a wire move. And when ions move, they are charged. So Na plus could move around just the same way an electron moves around in a wire. is why they're both charged. And that's why you get the cathode-anode experiment. Okay. So there are some ways you can draw electron structure as well. And these ways are kind of really common in the exams. So if you're going to draw sodium chloride again, we can stick with, or let's do magnesium oxide this time. You would do it like this. You'd show magnesium, because it's in group 2, it means it gets rid of 2 electrons. Okay, so magnesium would look like this. First electron shell, second electron shell, and that would be it, because you've got rid of the third electron shell. That's its whole goal. It got rid of the third electron shell so that it could be left with a full shell of 8 electrons. 1, 2, 3, 4, 5, 6, 7, 8. And to show that it's an ion, we do these square brackets around it. We put the plus there. We can't just leave it at plus, we need 2 plus, because it shows that 2 were taken from this outside shell that doesn't exist anymore. Okay, so we're drawing it as an ion. Before, it would have been drawn like this. The first shell, the second shell, and the third shell. The first shell would have 2, the second shell would have 8. And the last shell would have had 2. So those 2 have been destroyed. They are lost. And that is how we get to that drawing over there. Okay, so for sodium we do exactly the same thing if we were doing sodium chloride, that is, except obviously sodium's in group 1, which means it had 1 electron in the atom, and it will have 1 plus in the ion because it got rid of 1 electron. So for oxygen, this is on the other side, so this is a metal because it forms a positive ion, and because it's on the left side of the periodic table. And a non-metal is on the right side. Okay, and that includes oxygen. So with oxygen you get a 2 minus, it's in the 6th group, meaning it wants to add 2 electrons to get 8 electrons, which leaves us with 2 added negative charges. So we get 2 minus. Oxygen looks like this, so that's the actual oxygen. This is the first shell, second shell. Alright, so the first shell will have 2, because that's what first shells have, is full shells, 2. And this one will have 8 after it's become an ion, because it's stolen it to become an 8. Now, still use the square brackets in exactly the same way, only this time it's 2 minus. And it's an ion of a non-metal in group 6. So because it's group 6, it'll need 2 extra, which is what we've given it, and that's why it's 2 minus.